finding the displacement velocity and acceleration of a simple harmonic oscillator. Let's assume that we have a body or a particle moving along a circle with a uniform angular speed. Let's assume that by the time the body is here, radius from that is r. By the time it is here, it has a tangential speed, so that we can resolve this into vertical and horizontal components. So if we result it into horizontal component, we have a Vx. If we resolve it into vertical component, we will have this one, that is a Vy. But we want to liken it to the moving back and forth of a spring, for instance, undergoing simple harmonic motion. So by the time it is here, if we shine a light from below this way, by the time the body is here, we will find it here, and here is r, or x maximum, xm. By the time it will get here, the shadow will be cast here, minus r, or minus xm. So this is the center, here is 0. So that is set. So as we shine light this way from below, the bulb will be moving this way. As it's coming from here to this way, the shadow will be going this way. As it's going this way, the shadow will be going this way. So it will be doing this type of oscillation. If we shine a light from here to the left, the body will be doing, the shadow will be popping up and down like this. So by the time it's here, it will be here. By the time it's here, it will be here. By the time it's here, it will be here. So it will go this way. By the time it's here, it's here. By the time it's here, it's here. So the half cycle this way, it will come down. The half cycle this way, it will go up. The half cycle this way, it will go this way. Half cycle this way, it will go this way. So it can be likened that a simple harmonic motion. So remember, we said that it is moving with constant angular speed. So at an earlier time, say when the phase was just phi, there will be a time it was here, so phi will be 0 there. So at the time it was here, so at a later time it's now here. So it means that this angle, which is theta, we have earlier on in our previous video found out that the oscillation, since it's along x-axis, the oscillation x is the solution to that second order differential equation is of this form, omega t plus phi. It can be signed plus or minus. So for here we can say it's xm cos omega t plus phi. Any one you use, it will work. So that is the solution that we got. So that is for the displacement. So but for the velocity Vx along the x-axis, Vy will be along the y-axis. In order to get that, we just differentiate the displacement with respect to time. And if we call the whole of this z, we can actually see that it is a function of function by dt. And that means that if we differentiate this with respect to t, we get omega. If we should differentiate this whole thing with respect to z, because this thing is now z, we will get minus r sine z, if you like. Our Vx is equal to minus omega r sine omega t plus phi, because our z is omega t plus phi. So what this thing now means is that this implies that our V maximum is equal to minus omega r or minus omega xm, depending on what you have used. Remember, we have seen before that omega squared is equal to k over m. So if we put it here, that means that we'll get it to be minus square root of k over m xm, or minus square root of k over m r. So that is what we will get the V maximum. So that is that for the first one. For the acceleration, we will differentiate velocity along the x-axis with respect to time. And if we do the same thing that we did before, function of a function, so we will have this. So that when we differentiate z with respect to this, we have our w. If we differentiate this whole thing now, this whole thing with respect to that, we will have minus omega r. If you differentiate sign, you get cos z, if you like. So that we will now have that ax is equal to minus omega squared r cos z. Okay, cos omega t plus phi. That's what we will have. So this implies that our maximum acceleration is equal to minus omega squared r, or minus omega squared xm. Remember, we have said that omega squared is just a k over m r, or k over m xm. So no one it will work. And remember that if we do that, okay, if we say that this is equal to minus omega squared, this guy here, this whole thing is x. So we are correct that it's equal to minus, remember, k over mx, and this our acceleration is equal to d squared x over dt squared. So actually this is that equation that we solved in order to get this solution. So that means we are in order. So what this thing now means is that our velocity is moving between two extremums. That is between omega x, remember, omega xm, and minus omega xm. That's where this moving. Or you can just say, as we have been writing, omega r and minus omega r. Also, acceleration ax is moving between two maximums, extremums, omega squared xm and minus omega squared xm. So that is where they are moving from, omega squared r and minus omega squared r. Any which one will go. So that is exactly what we will get. So you see now from this thing that the acceleration am is pointing down. Acceleration a is pointing down. For instance, if it is this point along x-axis alone, it is pointing this way. But if you consider both the horizontal and vertical component, then it is pointing towards here, and you have a component this and a component. You have a vertical component pointing down this way, and also a horizontal component pointing down this way. This is a, and this is ax, and this one will be ay. So also we have vy and vx. So that is exactly how to do this.